Yeah, thank you very much for introduction. I'm super happy to open this workshop. Even though, as you know, Klaus should be here instead of me. Unfortunately, 2 weeks ago, he got into a pretty serious bike accident, but he's fine now, so he's already at home. And yesterday, he asked me to deliver you very warm greetings. So the topic of today is I'm going to talk about tunable 2D semiconductors and how realizing a quantum matter called graphene and how we use them to make new types of quantum devices. I'm sorry, it was a conversion from PowerPoint to OpenOffice in the last minute. It should be slightly shifted. All right. So first of all, I want to distinguish that our lab has 2 subgroups. So the first subgroup is working on a twisted graphene, the other group working on Bernal graphene. But what's common within them is we are working with quantum devices. We don't really study bulk properties of materials. So in the scope of twisted devices, it's mostly superconducting devices, of course, Josephson junctions, squids, rings. We are looking into copper pair boxes and the gate mounts. That's why very interesting to hear some news from MIT today, maybe tomorrow. However, in this talk, I will mostly focus on Bernal graphene devices, which you cannot go too far from making a QPC or quantum dot, because the main property of Bernal graphene is that you can open a gap here. Okay, so here I just outlined it 4 out of many platforms to host a superconducting processor, which recently showed a potential to be scaled up. So of course, some of the systems we know for long, such as superconducting qubits, and some systems are acquiring a lot of speed actually right now, such as Rydberg atoms and IO traps. However, when you talk about how to integrate a quantum matter into a quantum scope, we should look into the system called quantum dots, or what usually people think of like a spins, like how to use a spin to encode a qubit in a quantum dot. So we're gonna, of course, talk about this platform tonight. So looking back in the history of quantum dots, all this business started in 2003, 2004, when 2 groups in Delft and Harvard showed a coherent oscillation over spin in a gallium arsenide quantum dots. Because back then gallium arsenide was high enough quality and high availability. However, now we can say that silicon is the main workhorse of the field. However, devices looks pretty much the same as before. And one message I want to deliver you today is that perhaps graphene is a direction we should all look in future. Okay, so first of all, why carbon? Like, why do we want to make our quantum dots out of graphene? And the reason is pretty much the same as why people do it in silicon. The reason that carbon is a group 4 element was it's nuclear spin-free. In the same way as I'm talking about silicon 12, which is the most abundant isotope in nature. In the same way as the silicon 28, and as it was shown in silicon, as you purify your silicon more and more towards silicon 28, your coherence times going up. So in this way, carbon is very promising because we anticipate a very fine, very big hyperfine interaction. Also, a side note that T2 has actually never been measured in spin T2 in graphene devices. So, but I hope it's going to be measured very soon. And this benchmark will really put a graphene on a map in a spin qubit community. So another property which is in constant to silicon, which is, you can say it's an advancement of a carbon over silicon, is that carbon has a much lower atomic mass. meaning that the anticipated spin-over coupling should be weaker, meaning that it's harder to couple the charge noise to the spin degree on freedom. However, some of you may argue that if your qubit is protected from a charge noise, it's also protected from your attempts to manipulate it coherently, which is a fair point. Yeah.
What is the typical energy, the gap of the qubit? Because if you put the decay time by itself, it is a standard. You
What?
have to give me the typical energy scale of the qubit to understand if this is long time or not long time. So if it's
Typical scale defined by our electronics, 10 gigahertz. Like you cannot go, 10 gigahertz. Yeah. Also, for me, for experimentalists, it's very important that graphene, encapsulated graphene has really high mobility, so it's a really high quality quantum dots, which are really easy to tune and really easy to go to single carrier occupation. Also, carbon has a low effective mass. It's very similar to gallium arsenide, meaning that in contrast to silicon, you don't need to push your e-beam lithography to the limit to get very fine, very small gates. And for the topic of this talk, the most important property of graphene, that graphene has additional quantum number to spin, it's Valley. And Valley is a good quantum number in graphene, and Valley is a bad quantum number in silicon, as we will see later. And that's why we think, okay, we should make a new types of qubits using Valley degree of freedom, not spin degree of freedom, or maybe combining them. And these qubits are going to be better or worse, or yeah, we will see. So, all right, but when you think about, okay, I want to make a quantum qubit, I want to make a quantum dot out of graphene. Graphene is not a semiconductor, graphene is a semi-metal. The only point where it has a zero density of states is the charge neutrality point. So it's impossible to open a gap in single-layer graphene. And if you have no gap, you cannot confine your charge carriers into the quantum dot, meaning that there is no qubit. So the way to overcome it is use not a single sheet graphene, but a bilayer graphene, of a Bernal stack layer graphene. If you don't apply any external electric field, it's a semi-metal too, with a bit different dispersion. Instead of linear dispersion close to the charge neutrality point, it has a parabolic dispersion. However, if you break in invertible symmetry, if you apply electric field, so if you shift your carrier wave function from one layer to another, you can actually open a gap in the spectrum. So this phenomenon is like a textbook example how inversion symmetry can open your gap, and the spectrum is also known as a Higgs dispersion or some Brera dispersion because it looks like a hat. Shown here. The size of a gap is controllable by displacement field, so by how much voltage you can apply to back and the top gate. And this way, as experimentalists, you're really limited by how good is your insulator. And the size of a gap is the tens of millielectron volts. It can goes up to 100 and 120 millielectron volts. So it's enough to nowadays it was a huge progress in the last 5 years, and I will show why. So, but this is enough to get a really enough quality for material to host spin qubits. All right. Also, the spectrum, it has a funny shape like this. It's Higgs potential. It has some also non-trivial topological properties, but I'm not gonna talk about them much because I'm experimentalist and work with observable quantity. Right. So before talking about how we form dots in the graphene, I just briefly will walk you through how we fab devices itself. So how we use pretty standard stacking, dry stacking technique using PC-PDMS stamp. So we pick flake by flake and eventually put the resulting stack on a chip and put some context to it. So I will go in reverse. So we start with the graphite. So graphite is, so we use it as a backgate. Graphite, meaning it's a 5 to 20 layers of a graphene. And the most important thing is that it should be clean. It should be, it should be atomically flat. Because we notice if you use some metal or just a silicon substrate for your backgate, it's really hard to open a decent gap in your graphene. So then we use a layer of HBN as the insulator to insulate our backgate from our Bilayer graphene flake. And of course, we want some gates on it, so we put another layer of HBN to isolate Bilayer graphene from metal. In the next step, we put an ohmic contact to the graphene, which we do by the standard 1D context by just etching and putting metal to it, also contacting a backgate. And then we put the first layer of metallic gates, which are called the top gate, to form a 1D channel, where then we will form a quantum dots using the next layer of metallic gates, which are called the finger gates, this narrow metallic gates. So the resulting device looks something like this. This is a SEM image, so here you can see actually very hard to see flakes, but you can still see it. So graphene, HBN, backgate, and 2 layers of overlapping metallic gates on top. And of course, if you zoom in, so this is kind of the heart of the device, the channel where quantum dots are gonna live. So in principle, this geometry is very similar to divide to silicon, germanium, or other semiconductor quantum dot devices. Okay, so quantum dot is a zero-dimensional object. So of course, in order to make it zero-dimensional, you should start with a one-dimensional channel, which we form here by means of a so-called dual gating technique, where we apply voltage not only to the global backgate, but also to this huge, 2 huge split gates. And our goal here is to open a gap under the split gates, and not only open the gap, but also put a Fermi level inside the gap in order to form a 1D channel. So since we have 2 gates, top and bottom, so we have kind of both control on the size of the open gap, but also on the doping, also on electrostatic doping, meaning that we just can shift electrostatic potential up and down. So usually the first plot we acquire after the device is made, it's so-called gate-gate map, where we plot conductance through the channel as a function of backgate voltage and split gate voltage. And this diagonal line, you can see it's aligned with a really high resistance, so no current almost flowing from the channel, meaning that channel is formed. So by parking here, we know that we can start tuning our quantum dot further using this thin finger gate. So what finger gate does, it's tuning the chemical potential underneath it very locally. Yeah, very locally by means of a field effect. So imagine that you apply negative backgate voltage, so you accumulated holes everywhere in the device. Then you define the 1D channel, and then you start to apply positive voltage to one of the finger gates here. So when your carrier gas under the finger gate is the same, or also P is also holes accumulated, you will just see some conductance flowing through it, nothing spectacular. However, as you go more positive and you move your Fermi level in the gap under your finger gate, your current, of course, will go to 0. But if you will continue this process, at some point you will go to the N region very locally, meaning that nearby you're going to have 2 p-n junctions, which kind of naturally create a quantum dot, so-called PNP quantum dot. And the formation of quantum dot is very clear from this very sharp current or conductance peaks, which are called the column peaks. And each new peak manifests the fact that a new electron can occupy the quantum dot. So this is a very standard quantum dot charge physics, which most of you know, which you can see in a gallium arsenide and silicon germanium, but also in a graphene. So it just shows that the graphene has pretty much the same quality from the charge perspective. So for now, we didn't use the fact that graphene actually has a very rich and exotic spectrum arising from the fact that it has valleys. So let's talk about valleys and then come back to the quantum dots. So, of course, graphene is not the only material who has valleys. Silicon has 6 valleys, bulk silicon. And when you strain it in a narrow quantum well, as shown here, like silicon, germanium quantum well, only 2 valleys survive, and these valleys are located in the direction. In the same direction where your heterox structure is growing atom by atom. And unfortunately, in the same direction, you have this atomic interface disorder between 2 materials. And this disorder intrinsically couples your valley to your orbit, which is a super bad quantum number. And as a result, valleys are one of the biggest enemies of a silicon community, because once you, for example, hit your valley, once your Zeeman energy is equal to valley splitting, you immediately see that your relaxation time drops 4 orders of magnitude. So you want to really avoid your valley, and that's why people in silicon communities, they make quantum belts, for example, very thin to move your valley further in energy. So valley is a bad quantum number in silicon. But what about graphene? In graphene, everything is 2D, so your Berlenzon is also 2D, and your valleys separated an X and Y plane. And they also separated very far from each other, so the distance is a reciprocal vector, which is 1 over your lattice constant. It's a huge momentum. And the only scattering mechanism which can lead to such a momentum swing, to scattering from one valley to another, it's really an atomic defect. And as we know, the devices made by dry transfer and encapsulated, they're very flat. There is no sharp interfaces and no really atomic defects. It means that 2D valleys are really protected from the interface disorder, the main source of relaxation in silicon, meaning that the valley is a really good quantum number in graphene. So why don't we use it to make a qubit rather than spin? Yeah?
If there is no defect,
Yeah.
why is your mobility?
Oh, there are some defects, but you have a finite size. There are some defects. But we're talking about quantum dots, which is just 400 by 400 atoms. And on this scale, you can actually have atomically no defects. Thank you for the question. Yeah. In fact, just 1 year ago in our lab, it was demonstrated that when you make a singlet triplet qubits, singlet triplet T1 for valleys, indeed 1 order of magnitude longer than for spins. And the next idea was, and T1 for spin is also very good, 50 milliseconds. It's what state-of-the-art silicon qubits have with the artificial spin orbit. So our idea was, why don't we if a spin is a decent quantum number, valley is a very good quantum number, why don't we combine 2 to make a qubit which the only process which will lead to relaxation will be second order process. So this qubit should be super protected from environment, have a very long relaxation time. Okay, so before saying how we actually managed to demonstrate it, we need to, because I'm going to talk about spectrum of electron or hole in a single electron dot in graphene, we need to understand the spectrum, and it takes a few steps. It's very simple, but still takes a few steps. So we already know that we have, so our wave function of electron is a spinor. Not only we have a spin, we have also a valley. So we have a fourfold degenerate ground state, K minus spin up, K minus spin down, K plus spin up, K plus spin down. And if we don't have any magnetic moments other than spin, as a function of perpendicular magnetic field, the states would evolve just like this. You know, all spin down go up, all spin ups go down with a G factor of 2. Thankfully, it's not the case because I'm apologizing for the slides conversion. Because in the Berlenzon, we have a non-trivial Berry phase, which you can acquire if you go across one of the K points. In practice, you can summarize it as there is a valley G factor. meaning that as you increase magnetic field, your K plus values go up, your K minus values go down with a very high G factor of 10 to 30, which can also be tuned electrostatically. So now the spectrum looks like this, already a bit more interesting. However, it's not the end of the story, because also due to the hexagonal symmetry, there is intrinsic Kane-Meade spin-orbit coupling, which is a momentum-independent spin-orbit coupling, which just splits two Kramers pairs at zero magnetic field. Like it splits this four-fold state into doublets. And each doublet is called the Kramers pair, and the Kramers pair is the two states which are related with the time reversal symmetry, meaning that in order to go from one state to another, you need to flip not only the spin, but value too. And the splitting was experimentally measured many, many times, directly and not directly, and we know very well that it's something between 40 and 80 micro electron volts in Bilayer graphene. Okay, so the previous slide can be a bit theory heavy, orbit coupling, Berry phase. I mean, but you know, as an experimentalist, I believe in it because I just can see it every day in the experiment. I just make a device, I tune it to 0 to 1 hole or electron transition. At zero magnetic field, I see what I should see. I see ground state and just a single excited state. And as I increase, and then I do finite bias spectroscopy, meaning that just at finite bias, I measure, continue measuring conductance as a function of magnetic field. And what I see is exactly that each of states, it's not a single state, it's a doublet which evolves, which splits as a function of electromagnetic field with a very high G factor as expected. And you can literally just map your experimental data to your theoretical spectrum immediately. And now we can talk about the spectrum. It's actually very interesting because if you want to make a qubit out of it, so we're talking about ground state and a excited state, just as a function of magnetic field, you can go between different blockade regimes. So at a high magnetic field, you start with just the two spin lock states, this green and this purple state. They're just spin blocked, K minus down and K minus up. However, if you reduce your magnetic field, so you go before the crossing, this blue state and this purple state, they are spin value blocked. So these are two states from the Kramers pair. So that's why the historical reasons, if you want to make a qubit out of these two states, it's called the Kramers qubit. Yes?
Yeah. Could you just say something about the top line that is very intense and is not in this, correspond to this 4 that you are just explaining?
Oh, this way? It's a trivial line. It's just this side of a column diamond. It corresponds to electron going to left, to the left lead. Yeah, it has just a trivial charge origin. So, and this is a ground state and this is excited state, or tunneling to the same lead. Okay, so yeah, thank you for the question. Okay, so once we have the spectrum now, the goal is to compare the lifetime of a qubit made between green and purple state and between blue and purple state. And our anticipation was that lifetime of the later one should be much longer than of just a spin qubit made here. So this slide is just a very brief introduction of how to measure the lifetime of a qubit, a spin qubit of any excited state which you have in your quantum dot. It's called the Elzerman readout, developed in Delft in 2004. So it's just a free-level, very simple passing technique, which starts with initialization. When, for example, you have just a spin qubit, you have two states, so you just pulse both your levels before your Fermi level, to you lower to excited state or to ground state. And in the second step, you pulse your Fermi level in between your ground state and excited state. And if your electron is still in the excited state, it will tunnel away from the dot. Your dot for some time is going to be empty. And then at some point, your dot should be filled again with electron from the reservoir, which will tunnel to the ground state. However, if your dot is in the ground state during the second pulse, it will be just stay. Nothing will happen. It will stay in the ground state. And in the third pulse, you just pull all the states very far to reset your dot and just continue this again, and again to collect statistics. And so from experiment perspective, the difference between these two cases is going to be that you should have additional bump in your sensor current shown here, which will mean that your dot at some point was empty, meaning that your electron in the beginning of the second pulse was in excited state. And by measuring the probability of having this bump in your sensor signal as a function of waiting time after you load your electron, you can measure this exponential decay, and the exponential prefactor is going to be your lifetime. So for how long can electrons survive in the excited state. So in order to do this, we fabricated a device which has not a single quantum dot, but two quantum dots. One serves just as a charge sensor, which is capacity decoupled to the main quantum dot, and which serves just to monitor as a function of time the occupation of a dot. And in contrast to just simple spin qubits, we have more excited states. We have 3 excited states. I'm going to talk about only 2 lowest of them. So with the more excited states, we have more possibilities to put our readout level between different states to actually probe different types of relaxation from a different excited states. But the process experimentally is the same. We will just count number of times we have a blip in our sensor signal, like on this green trace, comparing to situation when we don't have a blip, like on a purple trace, and just to plot probability of it. You can also, for this device, you can notice that the loading time, so the time it takes for electron to tunnel in the dot here is very long. It's about 50 milliseconds, meaning that we managed to make a quantum dot which is highly decoupled from the leads. So the tunneling rate was about 20 hertz, meaning that only 20 electrons actually per second can enter your dot. In order to do it, you need to really push your barriers down, so you need really to confine your dots, which usually means that your spectrum changes comparing to when your barriers are super open so much that you can measure finite bias spectroscopy and to see spectrum, which I showed a few slides ago. So in this way, once we quenched barriers so hard, we wasn't sure if we still have this spectrum, this textbook spectrum, which we wanted to study. That's why we have to kind of remeasure it, but using a bit more convoluted single-shot spectroscopy technique, which I think was usually people used to just to calibrate the readout window, where you need to put your Fermi level between 2 states to do single-shot readout, which was introduced by Artem, I think, first time in 2010. And indeed, what we saw that we can see both excited states, and these excited states, as a function of magnetic field, they evolved the same way with a really high G factor and with a crossing point around 80 millitesla. And having this plot in a pocket, we had the freedom to measure the relaxation between the states which we wanted to actually probe and compare spin to spin value blockade by just kind of moving the readout level from here to here. So this step was quite essential. So let's start with just a spin blockade where at 135 millitesla. Very simple, just 2 states blocked by spin. So this excited state probability plotted as a function of loading time. Indeed, it's exponential, and T1 is 400 milliseconds, which is already very long, and the order of magnitude more than before ever measured in graphene. And the thing is due to the fact that the dot, we got dot which is really decoupled from the leads, so it doesn't feel electrons in the reservoirs. But this wasn't our goal. We actually wanted to move to a lower field and to probe these 2 states, purple and the blue one. And I want you to focus, don't look here, just to focus on this very shallow, slow decay of excess state probability as a function of loading time. And here as loading time goes all the way up to 12 seconds. And the resulting T1 time, which corresponds to relaxation between spin and valley log state, is 38 seconds plus minus 7. Of course, because it's really hard to measure such a long relaxation time, so you need to stop at some point. So indeed, spin and valley times 2 orders of magnitude longer than a spin time. And if you look at the kind of table of the longest T1 times ever measured, first of all, the funny thing is that the longest time was measured in gallium arsenide in Basel. And in this way, our result goes here as a second. But we don't think that 38 seconds is what limits our results, because what really limits it's how much time you can spend in the lab, because in order to acquire 38, like 1,000, 2,000 shots with the 38 seconds each, you need more than 15 hours, which is just not feasible. And also your device every few days and kind of can switch due to some random telegraph, very low frequency noise because of the semiconductor. All right. Also, as a function of magnetic field, we can nicely see how as we go lower in magnetic field over the crossing point, meaning we go from the spin blockade to spin and valley blockade, the T1 time just really sharply drops. There is also, you can see these black points, which corresponds to relaxation, which require either spin or valley blockade flip, which we cannot really distinguish. I'm not going to talk about it. We don't really understand some physics beyond around these hotspots. But just one point I want to make here is at zero magnetic field, we still measure 100 milliseconds of T1 with a 99.99% electrical readout fidelity, meaning that in principle you can make zero field spin or valley qubit if you know how to rotate it. Zero magnetic field. All right. So this way I'm already quite close to the finish. So I just want to go where we can go from here. So of course, the next step we want to do is to seek Rabi oscillation of the spin and valley qubit. Unfortunately, we don't really know how to drive it since it's so protected from the environment. There are a few things we're thinking about. First of all, of course, we can electrically tune valley G factor. And we can actually see it in experiment very clearly. If we can look at this transition between two excited states, K, which are valley blocked, K plus down and K minus down. And this is just a bias spectroscopy data where we go over this transition not as a function of magnetic field, but as a function of one of those big split gate voltages. So you need to change split gate voltage just by 2 millivolts in order to go over this transition. So this gives us a hope that by applying high frequency signal to this gate, we can actually maybe drive valley and maybe spin and valley too. Another interesting opportunity is to curve the quantum dot, to kind of make a dot living in a corner, in a geometrical corner. It's the kind of technique which was used in carbon nanotubes like 10 years ago, which will allow it to coherently drive the spin valley qubit. Because your G factor is so anisotropic, and by moving your dot in a corner, you can couple your orbital movement to your spin or valley degree of freedom. And the last point is maybe somehow manually introduce atomic defects, which will lead to direct scattering from one valley to another. Another interesting question we don't know answer on is how actually small is intervalley scattering, like how actually good valley as a quantum number. So far we only know that it is smaller than 2 nano electrovolts, which is very, very low energy scale. Usually your temperature of your experiment is 4 microelectronvolts if your setup is very, very good. So this is below any approachable temperatures of the experiment. So the only way to really measure it is same time resolved measurement, because 2 nanoelectronvolts is still 1 megahertz. This is very real frequency to measure doing some pulsing experiments, for example, like a charge qubit or a single triplet qubit, of course. Another interesting direction is to look not on the single carrier dot, but on the free carrier dot. Because free carrier dot is like a single carrier dot, but spectrum is inversed. Because it's like you remove one carrier from a full shell. And a full shell in graphene is has 4 carriers into it, right? And the interesting thing about it is that your ground state here and your next excited state, they are not moving away from each other as a function of magnetic field, but they rather move closer to each other. Meaning that here, if you want to make just a spin qubit, you can approach some kind of cheap frequencies for your experimental setup. You can, because 80 microelectron volts is at 20 gigahertz, and 20 gigahertz is already quite expensive setup, quite expensive tool you need to buy. Of course, as I already mentioned, there is a possibility to make a zero magnetic field spin and valley qubit. And the last one is, what about exchange? What if we have 2 spin valley qubits and we want to make a 2-qubit gate? So we know very well how a singlet-triplet exchange works, right? But what about valley exchange? If you have 2 dots with different valleys, is there going to be splitting, singlet-triplet valley splitting between them? Like, we don't know. But if there is, we can actually drive 2-qubit gates and swap operations very fast and very easily. Okay. On the side, there is another direction in Bilayer graphene activity in our lab, which is, I think, very interesting, and very soon we will see results from it very well. It's enhancing spin-orbit coupling using TMDs like tungsten selenide and tungsten selenide, tungsten detelluride, meaning the idea is that if you put a sheet of TMD next to Bilayer graphene, since it's a very heavy, tungsten is really heavy, so our hope is that we can actually induce spin-orbit coupling, like bigger spin-orbit coupling in the Bilayer graphene than we have intrinsic, in order to drive your spin qubit with some classical EDSR. And Jonas recently got a very nice results where indeed, by putting a TMD on your Bilayer sheet, you can increase your spin-orbit coupling more than 10 times, and shown here. But what's most importantly is that we can see that as we move our carriers away from TMD, by this displacement field, we can actually tune the spin orbit, so we can reduce spin orbit back to its intrinsic value as we move carriers away from TMD. And opposite, as we move it closer to TMD, we can see how spin orbit coupling is increasing. Okay. Another direction is capability of using these devices with a standard CQED architecture, meaning that we can couple quantum dots to microwave photons in a cavity. In this way, doing charge, spin, and Wally photon coupling. So we don't really know how to drive Wally now, but as far as we know, we can actually implement it here. Okay. And just a few words as my closing remark about our superconducting activity. So we recently just finished measuring a device made by Marta, which is a 4-layer twisted magic angle Josephson junction, shown here. So here you have 4 layers of graphene. So you can imagine it as a kind of 2 magic Bilayer graphenes on top of each other with a bit different twisting angle. And this device acting as a very normal Josephson junction, so we can clearly see very nice Fraunhofer pattern. And this gives us a hope. So since this looks good, so we want to study superconductivity devices a bit more. And as far as the question, like if you don't talking about Josephson, but it's just a normal superconducting interface, can we see Andreev reflection and transport? Because interfaces are supposed to be very clean and atomically flat.
I'm sorry.
Yeah.
Why did you put 4?
4? Sorry?
Why do you have 4 layers, not
4 layers. So you might, if you use 2, in order to get superconductivity, you really need to hit an angle. It really should be 1.08 to 1.12. And it's a bit more chill with 4. You can actually have a offset of 0.4 So it's not so demanding in terms of fabrication, so your yield is better. It's a bit longer to stack 4 comparing to 2, but almost all devices are actually superconducting.
Sorry, but let me ask you a question because I don't see well, getting old here.
Yeah.
So do you have, is zero net chirality or? So
How
is
looks the band structure? I think we wanted to know.
No, just chirality.
Chirality,
Plus
okay.
theta, minus theta, plus theta.
Yeah.
What is
So
that?
second and third are oriented the same. Second and fourth are oriented the same. Yeah, as shown here. And the second and the first and second twisted 1.7 degrees.
And how does the band structure look like?
Dispersive band,
Okay,
gap,
it's just
flat
one
band,
sample.
dispersive band.
Okay.
Yeah.
Excuse me, and the two in the middle, they are not twisted the magic angle.
Sorry?
The two layers in the middle, the twist angle is not necessary to get superconductivity.
No. You need to all angles should be all free angles. So you have free twisted angles. They should be within theoretically to get a flat band. Like we didn't have enough devices to get statistics how off can be your angle to. And also with the free angles we cannot measure them independently. So, but just talking about yield, looking at yield, 4 layers is easier than 2 layers. So surprisingly, it's more stable.
And suppose you use only 3 layers. Will you
3
get
layers
a
is.
pattern?
We didn't do it, but I heard that at other groups in Boston, it actually is the way to go.
Thank you.
One thing, another advantage of the 4 layers that as the most layers you put, the critical temperature goes up. The superconducting gap is bigger and bigger.
Uh-huh.
There is a limit to that.
There is limit.
There is a limit to that. So apparently about 5 layers or something like this, there is no real change. So just stick to 5 and that's pretty much the maximum you can get in terms of superconducting effect and critical field and
More questions? Yeah, we don't really study bulk properties. We're more interested into making devices with Josephson junctions, and also study. I just want to tell what our future plans. We made the Josephson junctions, so there's not too much you can do. Others, but we want to move a bit away from Josephson junctions and to study rather just a normal superconducting contact to see antireflection, maybe multiple antireflection, maybe hard gap, of course, Andreev bound states and how they're organized. Another very interesting question is how magic angle graphene superconducting is actually proximitize the normal graphene, how the induced superconductivity works there. There are no study about it so far. And of course vortices, because this is atomically flat superconductor, your field penetrates immediately, but other is vortices. We don't know, but we want to know. Okay, so I want to conclude saying that graphene is indeed, and I think I could a bit convince you this is, first of all, it's very clean and easy to work and to fab platform. The second thing is that this is truly hybrid because with the same material, just by twisting, even the same number of sheets, by just twisting it a bit, you can go from such a different structures, from Josephson junctions to spin qubits, which is amazing. And on top of it, you also have a trivial topology and additional to spin quantum numbers, which makes life, of course, more exciting. And for quantum electronics, the most important part is that all these properties are tuned by electrostatically by gate voltages. All right, so we have a lot of work to do, and we are very excited about future perspectives, and hopefully we have a very big and very talented team at ETHZ, and I want to say thank you to Klaus and Thomas In for managing such a big collective, and please ask me questions if you still have one, and thank you very much for your attention.